Chris Harris and I'm from AlleryTutors.com, and welcome to this video on exam papers. And this one is the AQA Chemistry Unit 5 June 2014 paper. So the whole point of this video is to go through the answers to this paper and give you some little hints and tips along the way to make sure you can successfully answer the exam questions. It is one thing knowing the content for chemistry, and another thing is actually trying to answer the questions in the first place. So it is a really important skill, and you've got to get used to answering the papers correctly. So that's what I hope to do with this video. It may be a good idea for you to try and get a hold of this paper. You can get it from the AQA website for free, and you can print them off, write your answers on, and then go back and check the answers on this video. And if you want to skip to a particular question rather than watch the whole thing, then there are some links to the left hand side that are appearing now, and if you just click on the links there, it will take you to a specific question. Okay, so let's make a start. Right, so we've got question number 1, and it shows us, or it's asking us, to write an equation for the process that has an enthalpy change equal to the electron affinity of chlorine. So because it's electron affinity, that means we're adding an electron. So all we have to do, basically this is just exam code for write an equation showing the electron affinity of chlorine. So we're going to put Cl. Now we have to put our state symbols down, and these are always in a gas phase. So we're going to add an electron, and all the elements, no matter what it is always in the gas phase. That's really important, and that will form Cl minus, and that's a gas. Okay, so that's not such a bad start. And if we look at the next question, it says, in terms of electrostatic forces, suggest why the electron affinity of fluorine has a negative value. So what we need to say is actually, because it's a negative value, that tells us that this is an exothermic reaction, so energy is given out. And the reason why energy is given out is because we have an attraction between the nucleus and the electron that we've just added. Because there's an attractive force there, then there's an excess energy, and that's released as heat. So this is a 2-mark question. So first of all, we need to say that there's an attraction between the nucleus, and that has the positive charge, and the electron. So because of this attractive force, we actually have energy is given out, or put released, and we can say, or we can describe this as exothermic. So that is the reason why. So any attractive force is going to be an exothermic process. Anything that's repulsive, obviously you need to put energy in to try and overcome that force of repulsion, so that would be an endothermic process. But this is exothermic because it's an attractive force. So you get 1 mark for saying this about the attraction between the nucleus and the electron, and you also get 1 mark for stating that energy is released and it's an exothermic reaction. Okay, right, so on to the next question. And so this is a Born-Haber cycle. And it says complete the Born-Haber cycle for silver fluoride by adding the missing species on the dotted lines. Right, so let's just have a quick overview as to what this is. As you can see here, we've got our solid silver fluoride compound, and we have the ions and the gaseous state here, and we also have some gaps here. So what we're going to do is work our way up and try and work out what's here. So this is the entropy of formation here, because we're forming elements, we're forming a compound from elements in their standard states. So all we have to do here is we have to add fluorine. Now fluorine is diatomic, which means it's bonded twice. You've got 2 fluorines, all halogens are diatomic, and it's a gas. That's the natural state it's in. But notice this is F2. We only need 1 fluorine, so we have to put a half just in there. Okay, and then if we go on to the next one up, now you can see here that the silver atom has been atomized. So this is atomization. So this has gone from a solid to a gas. So because this process has happened, we know that actually this line is just going to be the same as that because we haven't done anything to the fluorine. Okay, right, and then the next line up. So you can see here that we've ionized the silver. So we've removed an electron. So we have to put an electron here. And again, our fluorine isn't changed. We haven't done anything to that yet. So we just put half F2 gas. That's on the side there. Okay, and then the last step, actually here you can see the Ag plus gas, Ag plus gas. So nothing's changed there. However, we do need to form this, and we need to turn this into single fluorine ready for electron affinity. So we need to turn it away from F2, break the bond between it, and form just F on its own. So obviously we have the electron that's still there, that's still floating around, and we call this atomization or bond enthalpy, and this is fluorine gas. There you go. And what that's allowed us to do is to have the one fluorine, and then we electron affinitize to get to that stage. So this is 3 marks. You've got to know your steps. Just look at them really carefully. But the first mark comes in for these two here. So that gets to the first mark. You get a mark there and a mark there. So you get 3 marks in total for this question. Okay, right. So on to the next question. Right, so this one, you can see they've given us a table of data, and it says use the cycle in question 1C part 1 and the data in table 1 to calculate a value in kilojoules per mole for the bond enthalpy of the fluorine-fluorine bond. And you can see we've got 2 marks that's up for grabs here. So you can see we've got loads of different enthalpy changes and their values in kilojoules per mole. All we have to do is just use the cycle to work out the bond enthalpy of the fluorine-fluorine bond. So if I bring this cycle back in, there's our bond enthalpy there, and this is the one we're wanting to work out. So I'll just put that in purple, which is this one here. Now you can see this arrow is pointing upwards, so we need to get from here to here, but we can't get that way because we don't know the values. So it's a little bit like a roadblock, so you block the road. So what we have to do is we have to take a diversion, and we go via this route down here and up here to get to this step here. So what we're going to do is we're going to match these steps with the values on the table, and we're literally just going to write down the numbers. So if I just move that out of the way, so you can see this one is the this step here. So what we're going to do is we're going to look for the number, and this is the first ionization energy of silver. So you can see here this step. There you go. So we've ionized the silver. Now, because we're going against the arrow, because we're going to head down this way and go this way, we have to swap the sign. So the sign was plus 732, so now that needs to be minus 732. Okay, so if we come on to the next step, so we've done this step here, we'll just tick that off in purple, we've done that one, and we'll come to this one here. So this one is, if we have a look on our table, this one is actually the entropy of atomization of silver. So you can see here, this has been atomized. So if we go to the value, atomization of silver is plus 289, but we're going against the arrow, so that's going to be minus 289. Okay, and then if we go on to our next bit, so we've done this one. Okay, so then we have to go into this one, and we're going with the arrow here. This is the entropy of formation. So if we look for the entropy of formation in here, you can see that we have it there. There you go, entropy of formation of silver fluoride. Because we're going with the arrow, we just keep the sign the same. So that's going to be minus 203. Okay, and then if we bring this back in again, so now we're at this stage here. So we've done that one, and we're going to go back up to this arrow. So we're going with the arrow here. So this is going to be the lattice dissociation enthalpy. So if we look for lattice dissociation, there it is there. We're going with the arrow, so we keep the sign the same. So that's plus 955. And then we have our final one, which is this one here. So this is the electron affinity of fluorine. So we're adding the electron to fluorine. We're going against the arrow, so we change the sign. There's the electron affinity of fluorine. So that's plus 348. There you go, and that gets us to our last step. So if we bring in our calculator and if we work out our numbers, that's minus 732, minus 289, minus 203, plus 955, plus 348, and that should give us a value of 79, as you can see on there. Now 79 is actually the enthalpy value for half F2, because if we go back to our cycle, sorry, you can see here that this value here is for half F2, so that's not for the 1 mole of fluorine, which is what the bond enthalpy would suggest. So this is going to be for the enthalpy or the energy for half F2 is going to be 79. So for the bond enthalpy for 1 mole, which is what we need to work out, all we do is we double that, and we should get 158 kilojoules per mole. And there's our answer. So yeah, make sure you go through it and watch out for that little step there. You actually get 1 mark for this here, and you get 1 mark for that there. So that gets you 2 marks. Okay, right, so on to the next one. And so this is question 1D, and it says a theoretical value for the entropy of lattice dissociation can be calculated using a perfect ionic model. The theoretical entropy of lattice dissociation for silver fluoride is plus 870 kilojoules per mole. Explain why the theoretical entropy of lattice dissociation for silver fluoride is different from the experimental value that can be calculated using a Born-Haber cycle. Right, now what this is suggesting is that we have a theoretical value, so in theory we should have 870, but actually on our Born-Haber cycle, if I just bring back the data, the lattice dissociation entropy is actually 955. So this one's actually slightly higher than what it suggests in theory. So the reason for that is because actually we have we don't have a perfect ionic model, and this is what Born-Haber assumes. So the experimental value, I'm going to write this down on here. So the experimental value basically includes covalent interactions. Between the atoms. And effectively, what you could say is actually we do have ions because we know it is ionic, but there is some covalent character in there. Now, we obviously have some distorted ions, so instead of having perfect spheres like a positive and a negative ion, we actually have some slight distortion. So some of the electrons are now starting to merge in with the other ion next to it, and that is effectively a covalent bond, and that would change your value as well. So what we're saying is that actually in theory, so the theoretical value assumes a perfect ionic model with point charges and perfect spheres. Now, in the perfect world, that might be the case, but we don't live in a perfect world, and actually a lot of ionic compounds, the vast majority, do have an element of covalency in them as well, and obviously this has an effect on the value, and the more covalent character you have, the bigger the discrepancy in the value. So it's a classic question, and that's one of the biggest faults with Born-Haber is that it does assume a perfect ionic model, which of course doesn't really exist. So yes, you get 1 mark for saying this, and you get 1 mark for saying this. So about the experimental value includes covalent interaction, and then you're mentioning the assumption that we're making as well when we're doing Born-Haber. Okay, and on to the last bit of this question. So we'll just pull it up to there. Right, now it suggests, it says the theoretical entropy of lattice dissociation for silver chloride is plus 1770 kilojoules per mole. Explain why this value is less than the value for silver fluoride. So what we need to talk about is we're making a comparison between silver chloride and silver fluoride. And this comparison is to do with the size of the ion. And you can see chloride ion is bigger than a fluoride ion. So because of that, its charge density is actually a lot lower. So we're going to write that first. So we will put on there chloride ion is bigger, or you could say larger, than a fluoride ion. And effectively the chloride ion, because it's a lot bigger, they've both got the same charge, which is a -1 charge, but because the chloride ion is a lot bigger, the charge is spread over a larger area. So we can say that actually it has a lower charge density. Okay, and therefore, obviously, we need to explain this as well, why it's less. So we've stated what could be causing it, and we need to say why this is the case. And we just need to say that the attraction between the chloride ion attraction between the Ag+, which is the silver, and the Cl- ion is weaker, or you could say the attraction between the Ag+ and F- ion is stronger. So because of this reduced charge density in the ion, the attraction is not as great. So you get 2 marks for that as well. So 1 mark obviously for stating that one is bigger than the other, and therefore that has an effect on the attraction between them, and that gets to the 2nd mark. So there's 12 marks straight up for the first question. On to the next question. Okay, so this is question 2, and question 2 is all to do with enthalpy and entropy values. So it says table 2 shows some enthalpy change and entropy change data, and you can see they've given us a range of different reactions and the enthalpy and entropy values of them as well. And 2a says define the term enthalpy of hydration of an ion. Right, so this is just a definition, so you do really need to know these. So we'll write it down in here. So this is basically the enthalpy change when 1 mole of gaseous ions form aqueous ions. Okay, so the key things here is it's gaseous ions. This is when 1 mole of gaseous ions form aqueous ions. So this is a 2-mark question. Definitions you've just got to really remember. You know, they are important. They come up so many times. So gaseous ions obviously gets 1 mark for say 1 mole of gaseous ions, and that forms 1 mole of aqueous ions as well. So that gets you the 2nd mark there. Okay, so on to the next question. So this one says, use data from table 2, which is up here, to calculate a value for the enthalpy of hydration of the chloride ion. So enthalpy of hydration, we're just going to write down the equation first. So the enthalpy of solution, I'll write it in full. Okay, enthalpy of solution equals the enthalpy of the lattice. So this is obviously the structure, the full structure of your salt, plus, now this has to be the sum of the enthalpy of hydration. Now the reason why we put sum of is because actually we have 2 ions that can need to be hydrated. We've got the silver ion and we've got the chloride ion, sorry, as well. So we've got two ions that we need. So that sum of is actually really, really important. So we put sigma at the top there. Now, if we rearrange this, we need to work out, because the question was asking for the enthalpy of hydration, but just of the chloride ion. Because obviously we've got the silver ion as well, which have been given up here. So we need to bear that in mind when we come on to that later on. So basically the sum of the enthalpy of hydration equals the enthalpy of solution and we're going to subtract that away from the lattice enthalpy. So you can see that's all we've done, just rearrange that equation. Okay, so the first thing, obviously, we need to put our numbers in. Now we're looking for the enthalpy of solution. So if we come up here, our enthalpy of solution, as you can see in this data, is this one here, because there's our solid, and we're forming a solution, obviously, of aqueous ions. So we're going from a solid to aqueous ions. So this is the enthalpy of solution. So we're just going to put that number in there. Now that was plus 77. Okay, and the lattice value. So if I come back down to here, now the lattice value is this one. So this is our solid, and here's our ions in the gaseous state. So this is the enthalpy of the lattice, because obviously there's the ions. And again, you're supposed to know your definitions, so you can, if you know it, then you'll be able to spot it from there. So if we go back, so the lattice enthalpy is plus 905. Now, because this is a minus, I'm just going to put minus 905. Because we've got a minus sign there. And now if we put that into our calculator, just bring the calculator in. So that's just going to be 77 minus 905, and that's going to give us minus 828. So I'm going to put that there. Now, this is the sum of the enthalpy of hydration, this value here. We don't want to know the sum of enthalpy of hydration. We only need to know the hydration of the chloride ion. So we need to take into account the value of the enthalpy of hydration of the silver ion, and that one is this one here. So you can see this is 464. So obviously this is that number and the enthalpy of the chloride ion. So we need to take into account this number here. So we're going to add that number onto here to see what we've got left, and that should tell us the enthalpy of hydration of our chloride ion. So we're going to add the 464 to that, and if we bring in our calculator, there's our minus 828, and we're going to add 464 to that, and we end up with minus 364. And that is kilojoules per mole. Okay, so that gives you 2 marks. So you need to make sure you've got your marks in the right places. So you get 1 mark for actually working out your equation, and you get 1 mark for your answer. So that's where your 2 marks come in. And you can see that this thing is exothermic as well. And I'll just put that on there. So this is the delta H of the hydration of Cl- ions. Okay, so next question. So this is 2C, and it says suggest why hydration of the chloride ion is an exothermic process. So you can see this number was negative, and when we're dissolving it in water, water is actually a polar molecule, so that means it has delta positives and delta negatives. So the oxygen will be delta negative, and the hydrogen will be delta positive. And because it's polar, then effectively your chloride ion would be attracted towards the delta positive hydrogens on the water. And that means that because there's an attraction there, we have an exothermic reaction, and so energy is given out. So this is for 2 marks. So what we really need to say is we need to state that water is a polar molecule. Okay, so if I'm just going to draw a diagram just to illustrate this for you. So there's your delta positive, there's delta positive for your hydrogen, and your oxygen is delta negative, and your chloride ion, which is Cl minus, would be effectively attracted to the H plus, and this attraction means it's exothermic. So we're just going to write that in there for the 2nd mark. So the chloride ion is attracted to hydrogen in the water molecule. All right, okay. So yes, that gets you 2 marks. Relatively straightforward, not too bad. So you get your 1st mark there, and your 2nd mark comes in there. And so far we've got 6 marks in that 1st page. So not too bad. Okay, right. So I'm just gonna go on to the next one. We'll need the table as well for these questions. So this is a big question here. This one, as you can see, is worth 4 marks. So it says silver chloride is insoluble in water at room temperature. Use data from table 2 to calculate the temperature at which the dissolving of silver chloride in water becomes feasible. Comment on the significance of this temperature value. So this is quite a common question for them to ask. This is using Gibbs free energy, and basically you've got to know that for something to be feasible or just feasible, Gibbs free needs to be 0, and so that's the assumption that we're making here. So the first thing we have to do is 4 marks. You really need to write your equations before you write any numbers down, because you actually get a mark for that as well. So the equation that we need is delta G, and when it talks about feasibility, we're talking about delta G. Equals delta H, which is the enthalpy change, minus T delta S, which is entropy. This is temperature. Okay, now, like I say, we assumed that when a reaction is just feasible, becomes feasible, we say that the value of delta G equals 0. So we can completely disregard that out of the equation. We'll take that one out. And then we're wanting to work out the temperature at which this becomes feasible. So we need to rearrange our equation, and we should get T equals delta H over delta S. And so there's our rearranged equation. Okay, and then obviously we just need to put our numbers in after that. Now if we bring the table back over here, so the enthalpy value was plus 77, because this is the enthalpy when it dissolves, and this is the solid going into aqueous ions. Now this is in kilojoules per mole, and enthalpy values should be in joules per mole. So we have to multiply this number by 1,000 to get it to joules per mole. That's really important. A lot of people forget that. So it's an easy one to miss. So this is going to be 77,000 joules of energy, and we're going to divide that by delta S. So if we bring our table back again, delta S for that reaction was 33. This is already in joules per Kelvin per mole because it's entropy. So this is just going to be divided by 33, and we should get our final answer. So if we do 77,000 divided by 33, and that should give us this number here, and I'm just going to keep that to 4 significant figures. So that's 23333 Kelvin. Okay. So 2333, sorry. Okay, so that's in Kelvin. Right, and it's asked us for the significance of this temperature value here. Now, this is the temperature required to dissolve silver chloride in water. Now, you might look at that and think that's quite a big number, and it is. And actually, water boils at 373 Kelvin. So, actually, before you start to actually try and dissolve it, your water would evaporate, which isn't really very helpful. So, that's what's significant about it. So we need to say that water boils at 373 Kelvin, and this value, what we've worked out here, is above the boiling point of water, and it would evaporate. Okay, so that's obviously not very good at all, is it? So you need to get this thing to dissolve, and the temperature that you need to dissolve it at is obviously a lot higher than your water. So marks, this is worth 4 marks. So you get 1 mark for actually writing your equation. You get 1 mark for saying that delta G equals 0 for a reaction to be feasible, and you get 1 mark for your answer. That's the minimum temperature required for the reaction to dissolve, and obviously you get 1 mark for your significance of the temperature value. So that gets you the 4 marks. Okay, and then on to the last part of this. So it says, when silver fluoride dissolves in water at 25 degrees Celsius, the free energy change is minus 9 kilojoules per mole. So you use this information and the data from table 2 to calculate a value with units for the entropy change when silver fluoride dissolves in water at 25 degrees Celsius. Right, so what we have to do is we're taking obviously this equation, our delta G equals delta H minus T delta S, and we're going to rearrange that, and we need to work out, it's asking us to work out an entropy change. So we'll need to do delta S, and if we rearrange that, we get delta H minus delta G divided by T, and so there's our rearranged equation. Then what we have to do is just put our numbers in. So delta S, now the enthalpy change here, if we use table 2, so our enthalpy change is here. Now it's talking about silver fluoride, so the enthalpy change is minus 15. This is in kilojoules per mole. What I'm going to do is I'm just going to convert it into joules per mole, because the entropy value should be in joules anyway. So because it's in kilojoules, we'll do minus 15,000 joules. So we're going to put that there, minus 15,000 joules, and we're going to subtract that away from delta G. Now delta G is 9. Again, this is in kilojoules, so we're going to convert that into joules, so it's going to be 9,000. So a minus and a minus will give a plus, so that's going to be plus 9,000. There you go. Stick the brackets around there. Divide that by the temperature. This is at 25 degrees Celsius, so this is going to be 298 Kelvin. And if we put that into our calculator, we should get an entropy value. So let's just put that down there so we can see the number. Okay, so this is going to be minus 15,000. Oops, let's put that in brackets first, that would help. So minus 15,000 plus 9,000, and we're going to divide that by, and this is 298. Okay, press equals, and I've just made a bit of a mistake because I've multiplied the two numbers, so just bear with me. 15,000, and we're going to add 9,000, and we're going to divide that by 298. That's better. Okay, so we get minus 20 joules per Kelvin per mole. So minus 20, and entropy is always given in these units, joules per Kelvin per mole. Okay, so and I've given this to no decimal places because all of our other answers were given in that form as well. You can put it in kilojoules if you want. All you have to do is just do minus 15 plus 9 divided by 298, and that will give you in kilojoules per mole. However, it is good to keep the entropy values in joules. As long as you show your units, that's what you get the mark for anyway. So this is a 3-mark question. So you get 1 mark for showing your rearranged equation. So they're really important. You get 1 mark for substituting the numbers in there, making sure they're in the right form. And obviously you get 1 mark for your answer with units as well. If you don't have units, you lose that mark. So yeah, 13 marks, all on entropy. You do need to know your definitions. They're really important for these. They're absolutely vital, because if you don't know your definitions, you would struggle with the data in the table. And make sure you can rearrange them formulas as well, because that's very important. So 13 marks, unlucky for some, hopefully not for you. On to the next question. Okay, so this is question 3, and as you can see, this question is about some period 3 elements and their oxides. And it starts by saying, describe what you would observe when, in the absence of air, magnesium is heated strongly with water vapor at temperatures above 373 Kelvin. Right, equation for the reaction that occurs. So this is, they've been very specific here because you get different products depending on the conditions that you heat magnesium in. Now, this one said it was clearly in the absence of air, and you had water vapor, which means obviously the temperature is quite high, and rightly so, it's 373 degrees Kelvin, which is above boiling point. So our water is clearly in a vaporized state. Now, because it's when you heat magnesium with water, we actually get an oxide formed, not hydroxide. So we get magnesium oxide. So what we would observe would be a white powder, and the white powder would be your magnesium oxide. And also, just like with when you take magnesium and burn it in a Bunsen burner, you get a brilliant white flame. So we get two things here. So we get a bright white, well, not like a flame, but bright white light. It burns brightly. Okay. So it then also asks for an equation. So we just write our equation here. So this is magnesium, and we're going to react that with water, and that's going to produce magnesium oxide plus hydrogen. So this is really, really important that you've got to remember that, and don't be kind of tripped up by it. You don't really need state symbols. It's not really a requirement. Really, this equation should fit there because they've given us a space that I've just seen. So in terms of marks, you get 3 marks here. We get 1 for saying that a white powder is produced, 1 for bright white light, and 1 for obviously your final equation there. So it's 3 marks in total, so it's not bad. Okay, and on to the next question. So this is 3b. It says explain why magnesium has a higher melting point than sodium. So if we bring in our periodic table, now you can see that magnesium is in group 2 and sodium is in group 1. So we're saying, why does this have a higher melting point than sodium? And it's due to the fact that magnesium has a higher charge density, or the Mg2+, because we're talking about 2 metals here. So it has a higher charge density than sodium, and so therefore them sea of electrons that exist in metallic bonding would be held a lot more strongly. So let's write down our 2 marks, to structure this answer. So we're going to say that magnesium, or Mg2+, has a higher charge density than sodium. Right, now this is really important. We've got to make the comparison because they've made the comparison in the question, so they're expecting you to do the same in your answer. If you just said magnesium 2+ has a higher charge density, you wouldn't actually get the mark. So it's really, really important that you do make the comparison. You're very explicit in your answer as well. Okay, and we also need to say that because this has a higher charge density, as you can see, it's got an extra charge compared to sodium. Then it means that the sea of delocalized electrons are attracted more strongly. Okay, and this is because obviously, like you say, we have metallic bonding. Okay, right, so in terms of the marks, there's 2 marks up for grabs here. You get 1 mark for making this comparison that actually magnesium 2+ has a higher charge density than Na1+. So that gets the first mark, and the second mark is making that comment about the metallic bonding structure, the structure of metallic bonding. Okay, right, and on to the next question. So this one's worth 4 marks, so quite a few marks on this page. So state the structure of and bonding in silicon dioxide. Says other than a high melting point, give 2 physical properties of silicon dioxide that are characteristic of its structure and bonding. Right, now this is silicon dioxide. It is clearly a giant covalent structure. It is a little bit like diamond. It has a similar structure to that. So it's giant covalent. Also known as SAN, silicon dioxide, and you can make that into glass. Bonding, it's covalent, which is pretty easy mark really. If you knew that it was giant covalent, then obviously the type of bond has to be covalent. And the physical property, now it says that we have to give something other than a high melting point. We need to give 2 physical properties. So we're not talking about chemical reactions here. We're talking about how they physically are. So you could say that obviously sand is pretty hard. You could get marked for that, but it is brittle, and that is perfectly possible. Because it is hard, if you try and squash it in your fingers, it's very difficult to actually squash. But brittle because it's all in little grains, so it doesn't form big solid lumps of it. You could also put things like insoluble, because that's a physical property. Or you could put something like it's a non-conductor of electricity or heat. Conductor. So there you go. So I've given 4, but you only need 2 there, as you can see. So you can just take your pick, really. In terms of the marks, we get 1 mark for saying giant covalent. You can say macromolecular if you want. That would do. Bonding is covalent, and you get obviously 1 for your 1 each for your physical property. But like I say, you only need 2. So but I've written 4 there anyway. Okay, right. So on to the next question. So this is 3D. And it says, give the formula of the species in a sample of solid phosphorus 5 oxide and state the structure of and describe fully the bonding in this oxide. So the formula is P4O10. So that's for phosphorus 5 oxide. The structure, now this is molecular or simple molecular. So not giant, just a tiny little molecule. There's quite a few of them. So, and it also asks about the bonding. Now it is 4 marks. So obviously we've got 1, 2 there. So we need to talk about fully the bonding. So we need to talk about obviously the standard bond. This is a covalent. There are covalent bonds. And covalent bonds are between atoms. So there's your first type of bond. And then between these molecules, we have intermolecular forces as well. Now, it's difficult because phosphorus isn't horrendously electronegative. However, it does have a slight dipole there. So they would accept, obviously, that it will have van der Waals because it has electrons. So that's an obvious one. But they will accept dipole as well. So either or, really. Dipole. And these are forces rather than bonds, but it does say fully. So dipole forces, and these crucially are between molecules, and you must put that because it does say describe fully. So you have to say where these forces are, and they are between molecules. If you miss that bit out there, you'll actually lose the mark. So it is really, really important. So get to the habit of being specific with your answers. Okay, so the first one, obviously, you get 1 mark there, 1 mark for molecular, 1 mark for saying you've got covalent bonds between the atoms, and your 4th mark for saying that you've got these weak forces between the molecules. Okay, right, and on to the last 2 parts here. So we've got sulfur 4 oxide reacts with water to form a solution containing ions. Write an equation for this reaction. So this is a you've got kind of 2 possible answers here, really. You've got sulfur dioxide. Again, they've kind of told you what to write here. So sulfur dioxide. The reason why I know it's sulfur dioxide because the sulfur is +4, so that means we must have 2 oxygens bonding with that. So that's how we know it's SO2. And that reacts with water, which is H2O. That forms a solution containing ions. So you can either have 2 here. You can either have 2H plus SO3 minus 2 minus, sorry. So you can either have that one, or you could have H plus HSO3 minus. So you could have either one of them, and that would get you the mark. Okay. And then on to the last question. It says write an equation for the reaction between the acidic oxide, phosphorus 5 oxide, and the basic oxide, magnesium oxide. Right, so we've got a few different possible answers for this one. We'll start with this equation over here. So this is P4O10, and we're going to react that with magnesium oxide, because that's what the reaction was suggesting. And we're going to form magnesium phosphate. So make sure you get the formula right of this as well. Mg3PO4 2. Remember, your phosphate is 3 minus, and your magnesium is 2 plus. So you need 2 of these. That's what the 2 stands for. 2 of them to balance out your magnesium. Obviously, you can see that this is not balanced. So in terms of our phosphorus here, we've got a 2 there, but we have 4 over here. So we need to put a 2 there. And obviously, magnesium, we need to put 6 there to balance that, and that should be balanced. You can go for this one as well, which is P2O5, and this is going to react with magnesium oxide, obviously because that's your oxide, and you form the same thing, Mg3 PO42. Now you can see that this isn't balanced. We have 3 magnesiums here, so we need to put a 3 there, and that should balance the whole lot. So you should get there you go. You should get a mark for that one there, and you can write either one of these. In fact, you could probably even write it as ions as well. So you could even do Mg2 plus and PO4 3 minus if you wanted to write the ionic products as well. But they're the 2 main ones there. So you get 15 marks for that. So really important, really. You need to know your observations, a bit of how science works in this one, especially for this, what is a periodicity topic. But 15 marks, not too bad. On to the next question. Okay, so this is question 4, and this is to do with transition metal complexes, aqueous ions. So it says, consider the following reaction scheme that starts from aqueous CuH2O62 plus ions. So these are blue, your copper hexa aqua complex. Okay, and they've given us different reactions coming from our copper hexa aqua complex, which is this one here. And they've got reaction 1, reaction 2, reaction 3, and reaction 4. Now, they've given us the colours, but no formulas. Okay, says for each of the reactions 1 to 4, identify a suitable reagent, give the formula of the copper-containing species formed, and write an equation for the reaction. Okay, so we're going to start with reaction 1, which is this one here, and you can see we're forming a pale blue precipitate. Now, a precipitate is being formed, which suggests that we are adding a small amount of a base, so something like ammonia or something like sodium hydroxide, but we're only just adding a small amount. It's certainly not in excess. So the compound you would actually get would be copper H2O 4 OH2 square brackets, no charge on there, and effectively we've lost 2 of the water, or 2 of the water ligands are now OH ligands, so it's just with a small amount. So the equation for this, we're going to put everything in square brackets to show that it's a complex. So we've got H2O6, and we said that had a 2 plus charge because of the copper 2 plus. We're going to add 2 molecules of ammonia, and obviously we're going to form this complex here, the OH2, with no charge on the end, and we form 2 lots of NH4 plus. So there's your equation. Now, if you put hydroxide, it would just be the same with with OH minus, which goes along there. We need 2 of them as well, and we obviously form the same product, and instead here we'll form 2 lots of H2O. So either one of them, and you get a mark for each. So 1 for reagent, 1 for species, and 1 for equation. If you wrote the equation with that in there, they would actually combine. You would get 2 marks. So not to worry there. All right, okay, and then it then asks us for the same structure for question 2. So if we just go back up to here for reaction 2, sorry. So after you form this blue precipitate, it then forms a deep blue solution. So the precipitate redissolves from this. Now that's a classic sign of adding the same compound, but we are effectively adding more of it, and the precipitate redissolves. So we are forming a complex that is charged again, because neutral complexes like this, when they have no charge, they're insoluble. They don't dissolve in water. So if we keep on adding ammonia, then we effectively should form an excess. But the deep blue is actually quite significant as well. The deep blue suggests that it is ammonia that we're adding and not sodium hydroxide. So I'm just going to position up so we can see it. So the reagent here is excess, or you could say concentrated ammonia, which means pretty much the same thing. So you have a lot of it. And the copper containing complex. Now you've got to be careful with this one, because actually with some transition metal complexes, you actually go all the way and you completely displace all the ligands on the complex, but with this one you don't. And this, if I can write it properly, this actually forms a partial displacement. So we've still got 2 water ligands hanging on there, and the rest are displaced with 4 ammonias. Now, this whole thing, because that's neutral and that's neutral, has a 2+ charge. So yeah, you've got to be really careful with that. And the equation is Cu H2O 4 OH2, and we're going to add 4 lots of ammonia, and then 4 ammonia molecules will then displace the 2 hydroxides and 2 waters. So you're left with two axial water molecules as ligands. So obviously then we form our product. So I'll just quickly write this down. H2O2 NH3 4, close the brackets, 2+ charge, and we then actually form water as well, because that's what's left. So we need 2 waters, which go there, and 2 hydroxides, like I say, because we've lost 2 hydroxides and 2 waters. Okay, so in terms of the marks, you get 1 for saying that, 1 for saying that, and 1 for your product. And likewise, if you write this in your equation, you get these 2 can combine as well to form 2. Okay, so there's that one. Okay, and then you can notice that actually this compound, see where it was neutral there, and now it is charged. That's why this redissolves into solution, because anything charged allows it to dissolve in water. Okay, and then the next question is, again, it's just exactly the same structure, but look for reaction 3. So if we go back up to there, reaction 3 says we're going from this, or copper hexa aqua, to form a green-blue precipitate. The precipitate is really important, and green-blue, if you know your colours, you should realise that actually the reagent we're using here is a carbonate. So you can, any metal carbonate will do really. Sodium carbonate is the common one. You could use sodium hydrogen carbonate, anything like that, but this is probably the main one, so I'll stick with that. And the copper-containing species is actually copper carbonate. This is a 2+ charge, and so therefore 2+ ions, metal ions, always form carbonates when they react with a metal carbonate. And the equation would be Cu H2O6 2+ plus sodium carbonate, and that will form copper carbonate plus 6H2O plus 2Na. Now you can, I suppose, get rid of the sodium. It's just a spectator ion, and you can just put carbonate, CO3 2-, and they will accept that as well in the exam, and that will form the same thing, but obviously you won't have any sodium there because you've removed it from your equation. So again, you get 3 marks. You get 1 for your reagents, 1 for your species that's produced, and 1 for your equation. So there you go. Okay, so on to the next bit, which is 4D. Okay, so obviously 4D is looking at reaction 4. And so reaction 4, if we bring this back in, reaction 4 is actually going from your hexa aqua ion to a yellow-green solution. So this is a solution, so we know it's got to be charged still, and it is yellow-green as well, and that is a classic sign that you're adding a chloride into this, chloride ligand. So we need to add excess hydrochloric acid. That's probably the obvious one. Sodium chloride will work a little bit as well. And the complex that we form is the chloride is a big ligand, so it displaces all the water ligands on the original complex. We can only fit 4 of them around because it is a large ligand, so we can't fit 6 like the water ligands. So the equation is going to be Cu H2O6. That's going to be 2+ charge on the top there, plus your 4Cl minus, and that will form obviously your copper chloride CuCl4, 2- charge, because remember each chlorine has a negative charge. The copper's 2 plus, so if we have 4 of these, we end up with a 2 minus charge, which is obviously soluble. And then obviously we've displaced all of the waters from our complex there, so that's going to be 6H2O. And the marks, just as normal, 1 mark there, 1 mark there, and 1 mark there. So a boatload of transition metal complexes. You really have to know these as well. And the colours are important. I know they can be a bit of a pain, but you know, you get a good set of marks there, 12 marks, and if you can remember your colours, that's a valuable set of marks, especially in Unit 5. Okay, so on to the next question. Okay, so this is question 5, and question 5 is all about electrode potentials. So it starts off by saying table 3 shows some standard electrode potential data, and you can see they've given us a series of equations with E0 values attached to them as well. So it's give the conventional representation of the cell that is used to measure the standard electrode potential of iron as shown in table 3. So we need to know that to measure the electrode potential of iron, we need to use the standard hydrogen electrode, which is platinum, hydrogen, and H plus ions. And when we write our representation, we've got to put the most positive representation on the right and most negative. So the iron one is minus 0.44. The standard hydrogen electrode is 0.00 volts, because that's what the reference electrode is. So because that's the most positive, we put this on this side. So the electrode we use is platinum for the standard hydrogen electrode. We're also using hydrogen gas and H plus ions as well. And then we have our salt bridge that's connecting to our iron, which is Fe2 plus and Fe. So let me just explain what's happening here. So these lines here, the single lines, show a phase boundary. So you actually get a mark for putting in the correct phase boundary. So that's a metal to a gas to a solution. So they're different phases. So you put a line. If they weren't, you put commas if it's the same phase. And also that the most oxidized form must go nearest the salt bridge. So you can see here, this is an oxidation state of 0. This has an oxidation state of +1. So that's nearest the salt bridge. Likewise with that. So that's 0 and that's +2. So make sure that you set it up just like that. It's really important. And you get 1 mark for your phase boundaries. Like I say, put them in the right place. And you get 1 mark for putting your reagents in the right place as well. Okay. So if we move on to the next one. This one is question 5b. With reference to electrons, give the meaning of the term reducing agent. So a reducing agent is something that will donate electrons. So we call these electron donors. All right. Okay. So obviously that gets you 1 mark there as well. Okay. And then 5c. So I'll just move that there. It says identify the weakest reducing agent from the species in table 3 and explain how you deduced your answer. Right, now it is after a reducing agent. So this is something, like I say, that will that will give up electrons. So we're looking for something that is not very willing to give up electrons in this table. So if we just pull this down here, now these are all written in the reduced form, and this shows you basically the more positive this value is, the more likely the equation is going to go forward. So that means that these species are very likely to accept electrons, and what it's telling us is that the reverse is unlikely to donate electrons. So actually the weakest reducing agent in this case would be Cl2, because this positive value tells us that the reaction is more likely to actually accept electrons to produce chlorine and unlikely to go backwards. So because of this positive value. So out of these reagents, that would be chlorine as that reagent there. So we're just going to pull it up there. And so the species would be Cl2. And the reason it has the most positive E0 value. And when we refer to has, we're talking about the species on the right hand side. Okay, so that gets us 2 marks. So we get obviously 1 for writing chlorine and 1 for giving our explanation. So that's how you would work them out. Okay, right. So on to the next question. So it says, when HOCl acts as an oxidizing agent, one of the atoms in the molecules is reduced. Place a tick next to the atom that is reduced. So if I come back to this table here, now it's talking about HOCl. So there it is there, and chlorine. Now we know the oxidation state of chlorine is 0, and if we look at the oxidation state here of this chlorine, the oxygen is -2, the hydrogen is +1. So therefore the chlorine in this case is actually +1. So we're going from +1 to 0. So that shows reduction. So it's the chlorine that's been reduced. You can see the oxygen isn't because it's -2 there, and it's -2 there as well. And as likewise with the hydrogen, it's +1 there, it's +1 there. So the only one that's doing that is chlorine. So the answer here, you would just tick the box for chlorine. And then it says, explain your answer to question 5D part 1 in terms of the change in oxidation state of this atom. Well, we've already done that. So we can say that chlorine goes from, and we're going from chlorine +1 to chlorine 0. Okay, and so there's your mark there. Okay, and if we go on to the last question, which is 5E, it says, using the information given in table 3, deduce an equation for the redox reaction that would occur when hydroxide ions are added to HOCl. Okay, so what we need to do is we get our table, and we are doing the reaction of HOCl with hydroxide ions, which is this equation here. Now what we're going to do is we're going to do something called the Anti-Clockwise Rule, and this tells us the reaction that's feasible. And to do that, we need to put the most negative E0 on the top and the most positive on the bottom. So I'm going to write these two equations out just like that on there. So we're just going to write these out now. So it's going to be O2 plus 2H2O, and that's going to be plus 4 electrons, and that's going to produce 4OH minus. Okay, so that was our most negative, and then our most positive out of the two was this one, so 2HOCl plus 2H plus 2 electrons, and that will form Cl2 plus 2H2O. Okay, so you can see immediately that we have an imbalance, and we need to combine these equations. You can see we've got 4 electrons there and only 2 there, so we need to multiply this bottom one by 2. So that's going to leave us with 4 there. That's going to be a 4. That's going to be a 4. That's going to be a 2. And that one's going to be a 4. So we cancel these electrons out there, and then we rewrite out, and then we do our anti-clockwise rule. So we start, when we do the anti-clockwise rule, the most negatives at the top, we start the arrow from here and we go anti-clockwise. So we draw an arrow going from there to there, and an arrow going from there to there. And so that's going to help us to write out our full equation. So we're going to start from this side. So we're going to have 4OH minus, and we're going to add that to, and we start on the start of this arrow, 4HOCl plus 4H plus, which is this one here. The electrons are cancelled out, and we're going to produce O2 plus 2H2O plus 2Cl2 plus 4H2. You can do it an alternative way where you can flip this equation round back to front and then just combine your equations like that. But yeah, there's your answer. Now you get 2 marks for this. You actually get 1 mark for effectively showing this, this, and this being produced. Yes, this one should be H2O. There you go. Okay, so you can see we've got 4 H2O there. So that's 2 and 4, so they would combine to give 6 H2O. Okay, so yeah, so what we've got is this equation here, and that gets us the 2 marks. So that's 1 and that's 2 there. Okay, so on to the next question. next part of the question, should I say. Okay, so this is question 5F, and it says table 3 is repeated, so we've got the table again, the same data, and it says the half equations from table 3 that involve zinc and oxygen are simplified versions of those that occur in hearing aid cells. A simplified diagram of the hearing aid cell is shown in figure 1, so you can see there's our cell there. Okay, there you go. And then it says use the data from table 3 to calculate the EMF of this cell. So the EMF is basically we need to take the positive and subtract it away from the most negative. So you can see here that we've got a zinc and oxygen cell. So the most positive, there's your oxygen, and there's your zinc, and so the most positive is this one here, so we're going to put 0.4 first, so write that on there, 0.40, and we're going to subtract that away from minus 1.25. There you go. And so if we put that into our calculator, so it's 0.40 minus 1.25, and that should give us 1.65 volts. So there's our answer, 1.65 volts, and obviously that gets you the mark there. Okay, and then on to the next part. Okay, so this is 5F part 2. So use half equations from table 3 to construct an overall equation for the cell reaction. So if we come back onto this, and again we're going to do our anti-clockwise rule. So we're going to pick the most negative, which is this one here. So we're going to put that one on the top and this one on the bottom. So we're just going to write out our equation. So we're going to start with our zinc one. So we're just going to put zinc oxide plus water plus 2 electrons, and that will form zinc plus 2OH minus, and then we've got our oxygen one as well, so it's going to be O2 plus 2H2O plus 4 electrons, and that will produce 4 lots of OH minus. Okay, you can see that this equation isn't balanced. You'd see we need to cancel out our electrons. So I'm going to multiply this one by 2, this top row. So that's going to turn that into a 2, that's going to turn that into a 2, that's going to become a 4, that's going to become a 2, and that one's going to become a 4. And then we do our anti-clockwise rule and cancel out our electrons, because we're not supposed to have electrons in there. And we're going to write our equation. So anything on the right hand side here on this start of this arrow is going to be a reactant. So that's going to be 2Zn plus 4OH minus, which goes on like that. And then we're going to add that to O2 plus 2H2O. And that's going to produce our products. So our products are 2 lots of ZNO plus 2 lots of H2O, which is one of the products there, plus, and we've got 4OH minus. Right, now we can simplify this quite a lot actually, because we've got a lot of reagents left and right. So you can see we've got 4OH minus there, so we can get rid of that, and we can get rid of that. You can also see that we've got 2 waters there, and we've got 2 waters there, so we can cancel them out. And then we write our overall equation, because this is the overall reaction, which is effectively 2 lots of zinc, 2Zn, plus O2, and that will produce 2 lots of ZnO, which is zinc oxide. There you go. And all that would just get you 1 mark. Okay. Right. And then we're on to F part 3. It says identify which of A or B in figure 1 is the positive electrode and give a reason for your answer. So we're just going to bring that cell back in. So what we need to do is we need to look at A, which is the stainless steel lid, and B, which is the stainless steel can. And it did suggest which one is the positive electrode. So if we look on here, there's the positive value. We're looking for hydroxide. So there's the aqueous alkaline paste. That is the most positive E0. So therefore A would have to be the positive electrode. So you can see there's the positive E0, that contains the hydroxide, and that's attached to A. Okay, so I'm just going to put that in there. The positive electrode would be A, and the reason why is because the O2 electrode has the more positive E0 value. Alright, okay, so when I talk about the O2 electrode, I'm talking about this one here. So that's the one with the hydroxide in. So it's this one here, that's the most positive. Okay, so 2 marks there. So we get 1 for putting A and 1 for that one as well there. Okay, and then on to the last bit of this question here. Says suggest one reason other than cost why this type of cell is not recharged. And the simple answer is because the reaction can't be reversed. If it's a rechargeable battery, it means you can pass a current through the battery or through the chemicals, and it will push the reaction back to the original reactants. But with this one, actually the reaction can't be reversed, and effectively we can say that the zinc oxide can't be reduced by passing the current through it. Okay, and that would get you the mark there. So that's your last mark. Okay, so all of this is out of 14. It can be relatively straightforward. Make sure you know how to do your anti-clockwise rule because that can help quite a lot. And make sure you practice these. They are actually relatively straightforward, like I say, but you can get them quite confused when you think about reduction and oxidation and positive electrodes, etc. There's a lot of positives and minuses floating around here, so it can get a little bit confusing. But on to the next question. Okay, so this is question 6, and this is on hydrogen fuel cells. So it starts by saying hydrogen oxygen fuel cells are used to provide electrical energy for electric motors in vehicles. In a hydrogen oxygen fuel cell, a current is generated that can be used to drive an electric motor. Deduce half equations for the electrode reactions in a hydrogen oxygen fuel cell. So all we have to do is we just have to write down the equations that happens in these cells. So we'll start with hydrogen because that's one of the fuels that's produced. The hydrogen actually produces H+. So we've got 2 of them, and all we have to do is balance it with electrons. So you can see there's an imbalance here. There's 2 positive charge there, it's neutral there. So that's going to be 2 electrons there. And the other half equation is oxygen. That's the other thing that's fed in. And we actually produce water as a product of that. Now you can see we've got 2 oxygens there, so we need to stick a 2 in there to balance these out initially. You can see we've got 4 hydrogens there, so I need to put 4H+ there to balance that out. And then there's an imbalance in charge, that's neutral, that's positive by 4, so I need 4 electrons that go there. And so that gets you the 2 marks. So you get 1 mark for this and 1 mark for that. So there you go. So yeah, you do need to know these, and you are expected to be able to know what the products of these things are as well. Okay, so 6a part 2, use these half equations to explain how an electric current can be generated. So it's really simple, we just have to use them. So effectively what happens is the hydrogen is making the electrons, and the oxygen is receiving them, as you can see in these equations, and that is it. So put that on there. So the hydrogen makes the electrons, the oxygen accepts them. That's all you need to put. And you could be more specific, I suppose, but it's not a major marking point. We could say hydrogen electrode makes the electrons and the oxygen electrode accepts them. But as long as there's some link or reference to them equations that you've done there before, then that's effectively what happens. And this is obviously like a flow of electrons. So you get 1 mark there and 1 mark there. So there's another 2 marks. Okay. Next question. So 6b, and it says explain why a fuel cell does not need to be recharged. Now fuel cells are quite good because you don't need, like you say, you don't need to recharge them. So, but the only downside really is that you need a fuel to keep them going. And so I suppose the advantage of them not needing to be recharged is that you don't need to put a lot of energy in, but you do need hydrogen fuel continuously pushed into it. So that's the answer for this one. So that's hydrogen fuel. It's fed in continuously. There you go. Okay, so and that gets you, obviously that gets you the 1 mark there. So yeah, constant supply of hydrogen and it will keep working for you. Okay, and the next one, which is 6c, says to provide energy for a vehicle, hydrogen can be used in either in a fuel cell or in an internal combustion engine. It's just the main advantage of using hydrogen in a fuel cell rather than in an internal combustion engine. Now, when you're using a fuel cell, all of the hydrogen, or the vast majority of the hydrogen, is used to make the energy that you require. In a combustion engine, you've got a lot of moving parts, and a lot of the energy is used or is wasted through the actual moving parts of a combustion engine. So all you have to say really is that fuel cells are more efficient, and that's basically it. So more efficient. All right, okay, and so obviously that gets to that mark there as well. So far 2, 4, 5, 6 marks, not bad. Okay, and then on to the last bit for question 6. Put that question down there. There it is. Okay, this is 6D. It says identify one major hazard associated with the use of hydrogen oxygen fuel cell in a vehicle. So one of the probably more obvious ones is the fact that hydrogen is explosive, it's flammable. So we'll put that down there. Or you can say flammable. You could also argue, because you've got H plus signs in there and OH minus signs, you could argue that H plus or OH minus ions, that's the electrolyte, is corrosive. So anything like that, you only need one of them though. So as long as you got any one of them points, you should get your mark there. Okay, and that's it. It was a short question, 7 marks. Not too bad. Quite short answers and some how science works in there as well. Okay, on to the next question. Okay, so we're on to question B, or section B, should I say. And obviously this is the more difficult section. There's a lot less structure here. And this question 7, is mainly to do with transition metal chemistry, and there's a little bit of thermodynamics thrown in there as well. Okay, so we're just going to start with this question here. It says the characteristic properties of transition metals include colored ions, complex formation, and catalytic activity. It says consider the chromium complexes P and Q. So we've got complex P and complex Q, and it says explain with reference to oxidation states and electrical configurations why the chromium ions in complexes P and Q contain the same number of d electrons. You should not consider the electrons donated by the ligands. It says explain in terms of electrons why the complexes are different colors. And you are not required to explain why the observed colours are red, violet, and green. Okay, so we're just going to start by looking at obviously the first bit. Now it says with reference to oxidation states and electron configurations, why the chromium ions contain the same number of d electrons. So the first thing we'll do, obviously, we'll start and get our first mark. It's a 6-mark question. This is a lot of marks here. By saying that the oxidation states of chromium in P and Q is the same and it's actually +3. So you can see here it's +3 here, and it's still +3 here because we've got a chlorine ligand which is -1, and so therefore this is still +3. So there's your first mark, and it also asks us in electron configurations, and what we need to say there is that the electron configurations are the same. And actually what they have is they both have 3d3 valent electrons. So there's your first 2 points there, what we've addressed there. Okay, and we've also obviously considered why they have the same number of d electrons. On to the next bit, and it says explain in terms of electrons why the complexes are different colours. So now you need to understand about the d orbital splitting, because actually when you have different ligands that these do, the orbitals actually, now if I just draw like a diagram here just to show you, so you might have 1, 2, 3, 4, 5. So you might have electrons that sit in an orbital like that if it was just a transition metal on its own. But actually when we add ligands to it, the orbitals actually split, and they split into kind of 2 groups. So one has 3 and one has 2. And let's say for chromium it has 3 electrons in its d orbital. Actually what we can have is we have this. This is a delta E. So this is the energy gap between these, and how we see these as colours is effectively the electron will gain energy from a wavelength or frequency of light, and if it's the right frequency, it will have enough energy to get promoted up to the higher level of the d orbital, and then it will drop back down. And as it does that, it gives out a frequency or wavelength of light, so it's transmitted out from the complex, and this is effectively how it works. So we need to describe this in words. So the first thing I think we need to say is about the fact that we have different ligands. So I'm just going to put that on there. So we have different colours. Due to different ligands. So you can see on here we have 6 water ligands, and here we've got 5 water ligands, and we've got a chlorine one as well. So let's move that up. There you go, just so we can see that. Okay, so, and there's our electrons there. Here's our electrons, and there's the splitting, just in case you didn't see that just before, because I just realised it wasn't in the camera. So we have the 3 electrons in the chromium, and when they receive a frequency of light, the electrons get promoted to this higher energy level here, and then they effectively drop down and they give out this frequency of light, and that's what we're just describing here, just for those people who didn't see that on the camera. Okay, so obviously we've got different ligands, and this means the splitting of the d energy levels is different. So that's it there. So depending on the ligand will depend on how big that gap is there. So I'm just going to put that down in there as well. Okay. Splitting of d electron energy levels is different. Okay, right. And obviously, like you say, we have different wavelengths of light coming into this, into these electrons. So we'll put that down as well. There you go. Okay, so what we've got there is different wavelengths of light absorbed by the d electrons. So you get like a variety. Obviously, you get a spectrum of different wavelengths, and providing you get the right wavelength, this will jump up and then it will move back down, and it will transmit a frequency of light, and that's why we get the colour. So we'll just write that here. So different wavelengths, or you can say frequencies, wavelengths of light transmitted as a result. There you go. So quite a big question, a lot of marks. Let's just quickly go through the marks here. So we've got 1 mark for this, 1 mark for that, 1 mark for saying that we've got different colours due to different ligands, 1 for saying that we have the splitting of the d orbitals, and that will be different depending on the ligands. We get light that's been absorbed from just the surroundings, and then a frequency or wavelength of light is transmitted as a result. It's very important to use the word transmitted, because actually, rather than emitted, because the complex doesn't actually produce its own light. So we can't say emitted, but it does absorb a frequency of light, and then it transmits some of that energy that it received back out again as colours. Okay, so right, so this is our question. This is question 7. Okay, so let's look at the next question. Okay, right. So this is 7b, and it says write an equation to show how the cobalt NH3 2+ ion reacts with 1,2-diamino ethane. Explain the thermodynamic reasons why this reaction occurs. Okay, so what we have to do is we have to write an equation to show this. So we've got cobalt NH3 6, and that's got a 2+ charge, and we're going to react it with this 1,2-diamino ethane. Now this is a bidentate ligand, which means this can bond twice, as opposed to ammonia, which is just a monodentate or unidentate ligand, where it can only datively covalently bond once. So we can only have 3 of these. So I'm going to write that there: H2N CH2 CH2 NH2. Okay, so there's our ligand, and this is obviously going to produce this complex here, and this is going to be NH2 CH2 CH2 NH2, the big molecules, and a 2+ charge. There you go. And obviously we're going to our ammonias have been displaced. So there is our reaction there. Now you can imagine these things are quite big in comparison to these, which are quite small. We can only fit, well, we can fit 6 of these around the cobalt. Because these are too big, we can only fit 3 of them around, and that's why we've got a 3 there. Now it does talk about explain the thermodynamic reasons. So we need to talk about entropy, enthalpy, and we also need to talk about delta G as well. So we're going to start by looking at the entropy side, and you can see here that we have 4 particles on the left and 7 particles on the right. So we've actually got an increase in particle numbers. Okay, and this is going from, like I say, we had 4, and we'll go into 7. Okay, so and then what we have to do is then we have to talk about the entropy. So obviously we have an increase in entropy. There you go, an increase in entropy. And we need to talk about enthalpy as well. Now the enthalpy change here is actually pretty much 0. There is no net change in bond enthalpies. Now the reason why is because actually here we had cobalt bonding with nitrogen for the 6 ammonias, and in this one we've got cobalt bonding with nitrogen again, just in a slightly different molecule. So actually the bond strength is going to be pretty much the same. So that's why we don't have a change in enthalpy. And then the final comment is to talk about delta G. Now you probably might know that actually the equation for this is delta G equals delta H minus T delta S. So if we increase the value of delta S and delta H remains the same, then obviously we're taking a number and subtracting it by a bigger number, and so that's going to mean delta G is going to become negative, and that's good. Negative. So this means that the reaction is actually feasible, which is obviously a good thing. Which is obviously what we're after. Okay, so what we need to do is we need to assign our marks, and so we have 1 mark there. We have 1 mark for saying 4 to 7, 1 mark for saying increase in entropy, 1 mark for comment on entropy, and 1 mark for stating delta G. And you can see that's actually got us 5 marks there, which is pretty cool. Okay, so on to the next one. Right, so this is question 7 and 17, and it says the toxic complex cisplatin is an effective anti-cancer drug because it reacts with the DNA in cancer cells, preventing cell division. Draw the displayed structure of cisplatin. On your structure, show the value of one of the bond angles at platinum and state the charge, if any, on the complex. Right, now you've got to remember this. This is very important. So we're going to start by drawing platinum in the middle, and it's displayed. So we have to show every single bond, and cisplatin contains 2 NH3 groups and 2 chlorine groups. So there's a Cl there and there's a Cl there. So that's cisplatin. It's very important, these 2 ammonia molecules here, these 2 must be on the same side. They can't be opposite, otherwise that'll be transplatin. So it must be there. It can be flipped kind of the other way around, and that's fine, but it must be drawn with the 2 ammonia molecules and 2 chlorines side by side, right next to each other on one side of the platinum complex. Okay, so the bond angle, this is a square planar molecule, so the bond angle here would be 90 degrees, and the charge on this is no charge, because it has to state the charge. Okay, so platinum's +2, so there's no charge on there. So 3 marks, pretty straightforward, I suppose, where you work them out. So you've got 1 on there, you've got 1 there for bond angle, or 1 for stating the actual charge of it. Okay, right. So if we have a look at the next one, so this is C part 2. And it says, when cisplatin is ingested, an initial reaction involves one of the chloride ligands being replaced by water. Write an equation for this. Right, okay, so we're going to draw our cisplatin. So that's NH3, 2, PtCl2. We're going to react that with water. So like that. And now, what it's going to do is it's going to replace a negative chloride with a neutral water. So the charge of the complex is actually going to change. So we'll write this bit down first. So it's supposed to be NH3, 2, platinum, chlorine, water. Close off the brackets. Now, chlorine was had a negative charge, but your water is now neutral. So platinum is a +2 charge. Because we've lost the negative, the whole charge of the complex is actually positive. And obviously we have a Cl- as well, and there's your mark. Okay, and this bit, 7C part 3, says suggest how the risk associated with the use of this drug can be minimized. The simple answer is you just use it in small doses, or you don't use it regularly, so you maybe have it once a week or once a month or something. So otherwise the side effects could be quite severe. All right, okay, so let's have a look at the last bit for question 7. Okay, so you can see it says explain with the aid of equations how and why vanadium 5 oxide is used in the contact process. So the contact process is a method in which we can make sulfuric acid, and the main part of the contact process is to make sulfur trioxide, which is SO3. And without SO3, you wouldn't be able to make sulfuric acid, so it's very important. So what we need to do is write an equation to show how that's made, and you do need to remember this. So there's no real way of kind of working it out, I suppose. But this is vanadium 5 oxide, V2O5, and that's going to react with sulfur dioxide, and sometimes that's a byproduct of another reaction. And what happens is effectively this oxygen from here gets put onto here. So this turns into V2O4, and we produce sulfur trioxide, which is SO3. And then this here, so the second equation is this V2O4, which is here, will then react with half a mole of O2, and it will form V2O5 back again. And so there's the two equations regarding the contact process. So we've made our sulfur trioxide there. Now, what's actually happening here is this is acting as a catalyst, and so that's our next part of the answer. This acts as a catalyst. All right, okay. And obviously catalysts, they speed up the rate of reaction. And in this instance, we are speeding up the rate of reaction between the sulfur dioxide and oxygen, because effectively that's all we need. We just need them two to actually produce that, but we're using this as a catalyst. So speed up the rate of reaction between SO2 and oxygen as well. And we know it's a catalyst because there's your V2O5 and it's used up here, but then it's reformed at the end. So that's another classic sign that actually this is acting as a catalyst. All right, so just looking at the marks, we get 1 mark for this, 1 mark for that, 1 mark for saying it's a catalyst, and 1 mark for saying that it would speed up the rate of reaction. So yeah, a big chunk of marks. As you can see, there's 20 marks available there. You really do need to know your transition metal equations. There is quite a few of them, and it can be a bit of a pain to remember them, but you get a good chunk of marks, as you can see. Okay, on to the final question. Okay, so this is question 8, and question 8 is the final question on this paper, and this is a titration calculation. So it starts off by saying a student carried out an experiment to find out the mass of iron sulfate .7H2O of an impure sample of X. Now it says the student recorded the mass of X, and this sample was dissolved in water and made up to 250 centimeter cubed of solution. Says the student found that after an excess of acid had been added, 25 centimeters cubed of this solution reacted with 21.3 centimeters cubed of a 0.0150 moles per dm cubed solution of potassium dichromate. Use this information to calculate the value of the mass of iron sulfate .7H2O in the sample of X. So remember, the sample of X was made into a solution originally of 250 centimeters cubed. And effectively they've taken 25 centimeters cubed of this original solution and put it into a conical flask and titrated potassium dichromate from it. So that's the kind of overview. Now, there's a saying that I'd like to use, which is, if in doubt, work out the moles. So what we're going to do first is we are going to work out the moles. Obviously, I know what the answer is, so there's no doubt here. But if you were ever stuck, then that's normally the best place to start. Okay, so that is the first thing we're going to do actually, is work out the number of moles of potassium dichromate, or just the dichromate ion. So the potassium, it's a spectator ion, so we don't need to worry about that. So what we're going to do is we're just going to work out moles of Cr2O72 minus, and this is pretty straightforward because the moles is just concentration times volume. We have the concentration, that's 0.0150 times by the volume. The volume we used was 21.3. That has to be converted to decimeters cubed, so we divide by 1,000. So if I just put times 10 to the minus 3, that means exactly the same thing. So if we bring in our calculator at this point, so what we're going to do is we're going to put in 0.0150, multiply that by 21.3 times by 10 to the minus 3, and we should get our final answer of 3.195 times 10 to the minus 4. So put that in there. 3.195 times by 10 to the minus 4. Now, we need to know how many moles of iron 2 we have, because ultimately, if we know the moles of iron 2, we can then work out the mass of iron 2 that was in the original sample, and obviously the mass of iron 2 will also, the number of moles of iron 2 will also be the number of moles of this, because there's only one iron every one of these molecules. So what we need to do is we need to work out an equation, and we need to work out the molar ratio to work out the number of moles of iron 2. So we're going to start with the dichromate first. So dichromate is Cr2O7 2-, and that's going to reduce down to Cr3+. Now you've got to know that that's just a standard reaction. So now you can see here we've got 2 chromiums here and only 1 here. So the first thing you have to do is put a 2 in front there. We then balance with water next. So you can see we've got 7 oxygens there, and water is used to balance out any oxygens. So we need 7 H2O there. Then we add H+ to balance hydrogen. You can see we've got 14 hydrogens there. So to balance it, we need 14 on this side. We have to add H+. And then to balance it, we then balance it with electrons. You can see overall on this side, it is plus 12. And overall on this side, it is plus 6. So to make sure that both sides are the same, we add 6 electrons to this side over there. Okay, and then we obviously have iron. We have iron 2, Fe2+, and that's being oxidized to Fe3+, because this is an oxidizing agent. And we just need to balance it, and all we do is just stick an electron on the end there, and that balances it, so that one's a bit easier. Now, the number of electrons here and here is obviously not the same, so we have to multiply the bottom one by by 6. There you go. And that makes sure that we have 6 electrons there, so we have 6, 6, 6. And what that enables us to do is to cancel out these electrons. That's why I multiplied it by 6. And then what we do is we then combine our equation to get a full ionic equation. So we do Cr2O7 2- plus 14H plus 6Fe 2+ plus, and then your products 2Cr3 plus 6Fe3 plus 7H2O. Alright, so you can see here that this is our dichromate and there's our iron 2. So what we need to do is we need to identify the ratio, and it's important to write that down to be really clear to the examiner that you know what you're doing. So the ratio of Cr2O7 2- to Fe2 plus is a 1:6 ratio. So what that means is we can then work out the moles of Fe2 plus, and what that is, the number of moles of Fe2 plus is actually the number of moles of dichromate, which is 3.195 times by 10 to the minus 4. We multiply that by 6 because we've got a 1:6 ratio. If we put that in our calculator, there's our 3.195 times 10 to the minus 4. It's already in there. And we're going to multiply it by 6. And we should get this number here, 1.917 times by 10 to the minus 3. Alright, okay, so that's brilliant. That's the number of moles of Fe2+, but this is in the 25 centimeter cubed sample, because that's what we're titrating against. So we've got that amount of this in our conical flask. But the question did ask to work out calculate the mass of this in the sample X, and sample X was in a 250 centimeters cubed solution. So we need to work out the number of moles of this in the bigger flask, the original flask. So that's what we're going to do now. So the original moles in 250 centimeters cubed is, and all that is just this number here, 1.917 times by 10 to the minus 3, and we're going to multiply it by 10 because this is 25 centimeters cubed, and to work it out in 250 centimeters cubed, all we do is there's a factor of 10 between them. And you don't really need to calculate for this. There you go. Okay, so 1.917 times 10 to the minus 2 moles. And so this is the original number of moles of iron 2 plus in our flask, 250 centimeter cubed flask. Now, because the number of moles, that's the number of moles of Fe2 plus, that will also be the number of moles of this as well, because obviously the iron has only come from this molecule here. So what we can do there then is we can finally work out the mass of FeSO4.7H2O. So the mass is going to be the number of moles times by the MR. So the number of moles was 1.917 times by 10 to the minus 2. And we're going to multiply that by the molecular mass. So if you molecular mass of that with the 7 waters as well will be 277.9. And then if you put that into your calculator, so bring the calculator back in, so that's 1.917 times by 10 to the minus 2, multiply that by 277.9, and we should get a mass of 5.327. So what we'll do is round that up to 5.33. So that equals 5.33 grams. And there we go. And there you go. So you can see there's our equation there, or there's our setup. And we're going to just go through the marks there now. So you actually get 1 mark. Let's just check this. Okay. So you actually get 1 mark for working out this bit. And you get 1 mark for actually stating the ratio as 1 to 6. You get 1 mark for then working out the number of moles of Fe2+. You get a mark for working out the original number of moles, and then obviously 1 for your final mass, which would all add up to 5 marks. So not a bad set of marks there. They are quite common, these titration calculations, so it's worth getting plenty of practice in with them. All right, okay, and finally on to the last question. So this is 8b, and this is a little bit of how science works, just to finish off. And it's basically saying the student found that the calculated mass of FeSO4.7H2O was greater than the actual mass of the sample that had been weighed out. The student realized that this could be due to the nature of the impurity. Suggest one property of an impurity that would cause the calculated mass of FeSO4.7H2O in X to be greater than the actual mass of X. So what we want to do, effectively, if you're going to get the impression that it's going to be greater, in a practical way, we have to be adding more dichromate than we actually should do. And the impurity, to add more dichromate, that must mean that the impurity has to be reacting with the dichromate and using up more of it, giving you the false sense that you've actually got more Fe2+ ions. So the first mark here would be the impurity is a reducing agent that reacts with dichromate. Okay, so that would be like your first kind of idea, and this is one property. That's all it was after. And so, like I say, the impurity would react with more of the dichromate. There you go. It would react with more dichromate than a similar mass of FeSO4.7H2O. So yeah, it's how science works. You've got to think about it a little bit, and they're trying to link this practical problem and try and get to explain it using a bit of theory. So it's pretty difficult. You've got to really good think about that as well. But in terms of the marks, you actually get 1 mark for saying this, that the what the impurity is doing, and then saying what effect it would have practically. So you would actually react with more dichromate than a similar mass. So it's just a little short question at the end, 7 marks, but probably a very difficult one. The calculations you can easily get chewed up on a little bit. But just remember with the calculations that you need to work out the moles to start off with, and make sure you read the question very, very carefully and be methodical with your working out so it's really clear and show the examiners what you're doing. But that's the end of the paper. Bye-bye.